Oi, it's your boy SirDobbers. We're gonna make a tank today, okay? Okay. So we're not gonna be making any kind of tank like this. We're just gonna make a simple, quick and easy tank, hopefully, that focuses primarily on the functionality. And what that is everything besides the armor and all these outside props. So if I remove all these outside parented props, you see the core essentials of any tank. So let's get started here. The prop I'm going to be using is in Sprops. It's a 90 by 144 plate. Yep. And this is probably a good plate for like in my opinion, like a 25 to 30 ton tank. I'm going to go to transportation. I'm going to use wheel 40 for the wheels. Under wheel A, I'm going to use wheel 40. And rather than placing wheels directly on to the plate, I'm just going to move it using the precision tool. I'm going to move it in place because what we'll do is we'll access them later using axis center. And what I always do is I just stacker them to my liking. I've got behind, just freeze checked. Oops. Make 2 on that side, and then I'll go the other way as well. And I am going to use precision alignment to mirror them. Oops. And you can just as easily place them on the other side just the same, or you can go look up a tutorial on how to use precision alignment. Just for convenience, I'm just going to do that really quick. So now we've got our wheels on both sides. I'm going to no collide each one to each other. And then we're going to access them to the plate. And now I always have no collide checked. This way I don't have to no collide the wheel to the base prop when I place them all, because you will want them no collided. And all you will do with the axis center tool is click the side that you want it to be axised on. So we want it to rotate, around like this. So we're gonna use this side as the axis. Doesn't matter where you click it; it'll always take the center of the prop. And then I'm gonna click the prop I want it to axis to. Also does not matter where you click. So I'm gonna axis all these wheels. And I'm also going to make the plate weigh 2,000. You always want a sturdy base prop. 2,000 might be a lot, but that's just what I'm going to make it weigh for now. And when duping, same goes for everything. When testing, you always want to keep your main project that you're working on frozen at all times. So keep it in place. Dupe it if you want to test it. That's what I'm doing over here. And so you'll see each one of these wheels is moving independently of one another. So what we want them to do is all move at the same time, similar to how regular tracks would work on a tank. And so we're going to use the advanced ball socket tool to restrict the movement relative to another object. So have a look. Hopefully you can see all these values. All the X minimum for every single one is -0.1, and the X and maximum, for every single one, XYZ, is 0.1. We have free movement checked and no collide. I just have it unchecked because I already no collided everything. And now we will just ball socket them each to each other down in the line. I'm going to dupe it to test it again, or just to show what that did. And now you can see each wheel is moving, you know, the same way that each other wheel is moving, or at the same speed. So I went ahead and placed my seat near the back of the tank, just because I kind of prefer the engine in the front and the ammo in the back. And so it's just personal preference. That's how I'm going to do it for this tutorial. So now comes the hard part, which has to do with gear boxes and gear ratios and engines and such. So the first thing I'd like to point out is the relationship between the length, width, and overall weight of your tank. So the longer your tank is going to be, and skinnier the tank is, so if you have a whole bunch of wheels here, the harder it's going to be to turn in place, or even at low speeds, to turn at all, really. And so you will really need a lot of torque. And so it's always good to have good proportions like this. So you know, this is almost like a square. That'll be the easiest to turn. We've only got 5 wheels, and it's a really small tank, so we shouldn't have no problem. But if you think about it, if we have a long tank here, the only way this can turn is for all these wheels to push in one direction this way, and if all these push in the other direction, or they don't move at all. So you only have one force acting on the tank, which is in this direction, which isn't really an ideal way to turn. You know, cars, all they have to do is turn and point the direction they want to go to turn. But the longer we have of a tank, the more these wheels are going to work against each other when the tank is trying to turn. So that's something to think about when making a tank. So now we'll get into the engine. The engine I'm going to use is an 11-liter i3 diesel engine. Go to the ACF menu here, go find it. Mobility, engines, i3, 11-liter diesel. I'm just going to put it on its side just so it fits, and leave it where it is. And as for the gearbox, we're going to go to Mobility, Gearboxes, CVT, and CVT Transaxle Large Dual Clutch. And if we were to place and use a medium CVT, you can look at this and you see how it says torque rating 650. You always have to make sure the torque rating is high enough to suit your engine. So the engine here is only has 1100 Newton meters. I shouldn't say only, but it has 1100 Newton meters. Whereas this medium gearbox has a torque rating of 650. That doesn't cover it. It's too small. And if we go one step up to the large, you know, this one goes all the way up to 6,000 torque rating, but it'll do. It's the only one that will work. And so I'm just gonna place this close to the center of the tank. You want to look for the center of your wheels. That's where I will put my connection, just so you know, these wheels have less stress than if you were to put the connection in the front or back. So line that up as best you can. I'm just gonna eye it like that. I'll no collide it first. That's a good idea. That's good. That's good. Put it somewhere in the center. Weld everything down. And then to connect everything, we'll take the ACF menu tool, right-click the engine, and then right-click the gearbox. Right-click the gearbox, right-click the wheel. and do the same for the other wheel, and now we have all the connections that we need. Now we'll start placing our wire components. Alright, so the first thing we're going to put on there is a pod controller under vehicle control, and we're going to link that up to the seat. And then next we will start writing going through an expression I've made for tank movement. So I'm going to go over this line by line and try to explain to the best of my ability what each thing does. So the first thing we'll go over are the inputs. We have two inputs, pod and CVT. So that's the pod controller and then the gearbox. And these types of inputs are going to be a wire link input. And what wire link does is it allows for calling of inputs and outputs within the chip, rather than, for example, writing W, A, S, and D and inputting them all, wiring them all up. You can just call them from within the chip, which is what we're doing. Okay. So secondly, we have our outputs. We've got throttle, and then WL, it stands for weld latch, and that's just for if the tank is, not moving or braking, you can weld the wheels together. We'll stop on a dime. Anyway. So, interval 50, that's how often the chip is refreshing, and 50 is 20 times a second, I think. Alright. So anyway, after we have our inputs wired up, now we're going to start doing functionality. So now, rather than calling an input, rather than calling an output, we're gonna tell an input of the CVT gearbox to do a certain thing. So we want the left clutch on the CVT gearbox here. We want the left clutch to enable when the pod controller, when we press Alt. So that's just like the clutch, the typical clutch key that I use. So we want it to activate when we press Alt, and we want it to activate it when we press D. We've already declared D over here, so we can just write it as D. Now, just like the left clutch, the right clutch we want to activate when we press Alt, as well as when we press A. For turning, what we're going to have is for example, if I press A, we're going to have these wheels not move, and these wheels push forward. Now we'll rotate. So this can't turn in place, but it can probably still turn. Okay, so now that we've got the right clutch and left clutch wired up, now we're going to do left brake and right brake. Left brake equals D, right brake equals A. So it's basically the same exact thing on left clutch here, except we don't have Alt. So now comes throttle in the engine. The way I write my chips are kind of strange. I like to use just arithmetic rather than if statements. So the same thing can be achieved by writing, for example, if A, then right brake equals 1. But this is just the arithmetic way of doing it. So throttle here is going to equal W plus A plus, oh my gosh, can't read. W plus S plus A plus D. Times 100, and the only reason I clamped this is so that it will always be 100. So it's kind of a weird way to do it, but go ahead and just copy that. CVT gear, we're going to have it always be 1, unless you press S, which then it will add 1 when you're pressing S, so it will equal 2. And if we look at our gear box, we have gear 2 equals negative 0.1. So it'll rotate the rotation of everything, since it's negative, if we're in gear 2. And S will make us, go backwards, and it'll also make us go to gear 2. Alright, now comes the CVT ratio part, and this is the part that's kind of tricky. Speed will always have the absolute value of the entity's local velocity in the x direction. And so what that does is when I place a chip, I'm going to place them up here. When I place a chip, depending on where this is facing, make sure this is always facing the front. And if it's not, if I place it down and it's facing sideways, what you'll do is you'll just unweld, well, make sure it's frozen first, sorry, freeze it, unweld, and then take your easy precision tool and just rotate it 90 degrees. Make sure it's on rotate. Rotate 90 degrees, right? And then once it's rotated in the right direction, just weld it back. So the speed in the local x direction is this way. So however fast this chip is changing speed, that's what speed will be. And now let's skip MoleInitial for now. Let's go ahead and just put them in as you see them. I'm going to have this as 4,000 and initial as 0.1. But CVT ratio equals speed divided by mole plus initial. And so what this accomplishes is what the CVT does is it changes gear ratios as you move the tank. So that makes it so you have, for example, a low gear ratio, which provides more torque when you're at low speeds, and a higher gear ratio when you're at higher speeds to provide lesser torque but more power. Okay, so we have our speed. That's just a constant. Mole is 4,000. Now this can vary probably from 2,000 to around 6,000, and you just have to try to get it figured out. And the faster or the higher this number, the quicker your tank will reach maximum RPM and will reach its top speed. The lower will provide for a higher range of movement with less power. So you'll have less torque, but you will perhaps move much faster and like get up to higher speeds. So that you have to figure out what your tank can handle. And now initial, this is typically from around 0.01 to 0.1. And this provides an initial gear ratio for your tank to start out in. So at speed 0, this is obviously going to be 0. So you still want an initial gear ratio to get your tank moving. The lower this is, the more torque you'll have. The higher it is, the less torque you'll have. So using this would be, at this end of the scale will be for really heavy tanks, and this may be for really light tanks, and this can go higher. It just depends on probably around these values here. Lastly, we have our weld latch equals space plus not active. Is important. So we've got pod, active, normal. Normal just, if I haven't mentioned, normal is just declaring what kind of variable it is. So it's not like a vector or a string. It's just a regular number. This exclamation mark is not, so when it's not active, this will equal 1, and then over here, if you just press space, this will also equal 1. And that's our chip. So hopefully you can copy that or understand it or whatever. We'll start wiring everything up. We're going to take our wire tool. Pod goes to the pod controller wire length variable. CVT goes to the CVT's wire length output. Throttle in the engine will go to throttle. And we're just not going to worry about weld latches to begin with. Active for the engine, we'll wire that to active in the pod controller. So when you get in the seat, the engine will turn on, basically. So now let's dupe it and test it out. Hop in, and surprisingly, it's actually working pretty nicely. I mean, for the weight class, you remember this plate is only 2,000. Normally, you're gonna have, you know, up to like a 50 ton tank that's armored. So it's gonna weigh it down quite a bit. But this is working just fine. Let's hop out and adjust the variables really quick to give an example of what they might do. So let's change initial to, let's keep initial where it is, and we'll change the multiplier to 6,000, pretty high. So this will give more torque at lower speeds, and so it might not even be able to reach high speeds anymore. It's going to reach higher RPM. You can hear the engine already revving up higher. So 6,000, I would say, is actually more optimal for this weight of a tank, because you're going to get these higher RPMs at this speed, and lower torque, or more torque at lower speeds. So let's remove that, and I'm going to start putting armor on this thing. So you're going to use a door here. Just kidding. Let's not use a door. Let's go to Sprops. So this is a rectangle prop, 42 by 90. Put that on there however you like. Make sure it's no collided, because we'll be parenting all these props later. You want them all to be no collided, otherwise bad things happen. Just remember that. So this is our armor. This is our frontal armor. Let's add some rear armor. So go ahead and just do the same thing, or use precision alignment to just quickly do that. Now we've got our armor. And now before I weld anything or do any constraints, remember, make sure it's no collided. Doing good. Let's parent these. Parenting is very important. So we've got to have this multi-parent tool right here, multi-parent. And what you want to do, especially in regards to tanks and vehicles, in order to edit parented props, so for example, the weight, color, material, or if you want it to be removed, you have to parent everything to a wire chip or gate or entity of some sort. So I just use a gate, any gate, it doesn't matter. We're just placing one just to have something we can parent everything to. So I've just got an add gate here that I'm just going to put somewhere on the tank. Doesn't matter where, really. Take our multi-parent, click the first prop, click the second prop, right click the chip, and now you'll see what that does. That makes it so these plates, the parenting does exactly what it says. It finds a parent prop and then just mimics all of its movement, basically. So the physical aspects of these no longer exist. You can't run into them. You can't even, the ground can't even hit them. You can't put any constraints on them. It's purely for show. But it is not purely for show when it comes to ACF, because ACF does not go through plates. This is how you armor tanks. And so I'm going to take out our armor, ACF armor properties. Our thickness, let's make this frontal plate 100, and since it's at a 90-degree angle, we've got no potential for bouncing or no increased in effective armor. So let's go with 180 frontal. Ductility, I'll go over what that is later. I'm going to make the back the exact same armor value. Now if we hop in, also if you take your armor properties and press R on your tank, you can see the total weight. So right now it's 13 tons. So you can already tell it's off to a really slow start. So we'll have to adjust some values here to get this thing to work a little better at lower speeds. We need it to have more torque. And what you can do is go into your gearbox. So we have the CVT dual clutch transaxle, and make sure these values are always the same. So our target RPM is not 3,000 to 5,000. It's 650 to 1,800. That's what this says. So what I did there was I just changed the target RPM, you can see it in line 2 there, to the same as the power band. The power band, this generally provides 650 to 1,800 RPM. So that's what this is going for. And now what we were originally going to change was the final drive, which just is like a multiplier for the entire thing. So I'm going to bring that down. The lower the value, the higher the torque. So I brought it down a bit to 0.7. Give it another test. Well, you can tell it's doing a little better. It's doing a little better. And now rather than lowering that anymore, because the lower you get, the more kind of glitchy it starts to get, I'm going to change the initial torque value 10 times lower. So that's quite a lot lower, but that's what I'm going to do. So I'm going to change it to 0.01. Now we should get a lot of torque at the very start when we're not moving. Look at that. That's too much torque. See? Let's go with 0.05. That looks just about right. Turns pretty nicely. And we've got our lovely armor in the front, protecting us from anything. And let's, one more time, go over the armor. So you can see it says 180 armor. This, for some reason when I'm recording the screen here, kind of glitches out, but you can see the weight. If you focus, it says 3,900. As you change armor values, so if I go to like 280, that like doubles. So now we're at like 6,000 mass, 6,000 weight, but a lot of armor, and still only 123 health. Ductility, by the way, changes armor to health ratio to weight. So high ductility, we'll put high health on that, but make it weigh 2,000 more. Low ductility, we'll put low health on that, only 24 health, but it only weighs 2,700. So we'll keep that just at 0. Don't mind him, I guess. I'm going to increase the weight of both of these to a whole bunch. And right click, we've got a 20-ton tank now. That's what we were going for. So think of it this way: all the armor that you put on your tank, this tank should probably only weigh around 20 tons. I'm just putting all the armor just in the front and the back, which is obviously not ideal, but for this tutorial, that's what I'm doing. Got to change our values over here. So let's keep the initial torque to 0.05. Multiplier 6,000. That's probably good. And let's see if it drives. So it can't really turn in place. I mean, it can turn, but it doesn't turn in place, and it turns fairly slowly. But it's doing its job, you know. Start to go, and look, we're going actually pretty fast, I would say, for what we've made. Turns a little quicker at high speeds. And there, you've got your first tank body. And I'd like to end this first tutorial with that. And you can mess around, try to get a working body, and I will come out with another tutorial regarding the turret. So to review, what I always do typically is I would model it first, so we don't have anything in the way. We know our armor class. We have everything parented. That's what I do first. So I would place all these props that I want wherever I want them. Got some super badass side armor here, and now we've got some super badass top armor. And make sure everything's no collided. Parent everything to that chip. And once you're done with that, you can start adding wheels. You can start adding functionality, and start messing around with the multipliers and this CVT final drive. Alright guys, if you're interested in seeing anything, or if you have any questions, let me know in the comments. Otherwise, I'll catch you in the next video. Thanks for watching.